Imagine you're a student, staring at a complex diagram in your textbook. You need to understand it, to recognize the key components and their relationships. Now, imagine an AI-powered study tool that could instantly highlight those components, explain them, and even quiz you on them. How does it do that? How does a computer recognize anything at all? Let's take a simpler, but equally profound, example. Look at this handwritten digit, a 7. To you, it's immediately obvious. But what does it mean for a computer to recognize this specific squiggle as a 7? It's not magic, it's a series of logical steps, built on fundamental principles. This ability to recognize patterns is the bedrock of almost every AI-powered study tool we see today. From smart flashcards that adapt to your learning style, to essay graders that provide instant feedback, to tools that summarize complex articles, they all rely on the computer's capacity to interpret and understand information, much like recognizing this 7. To understand how this works, we need to strip away the complexity and start with the absolute basics. How does a computer even see this 7 in the first place? It doesn't see lines and curves like we do. It sees numbers. Imagine each tiny square in this grid is a pixel. If a pixel is part of the 7, it's dark. If it's background, it's light. We can represent this numerically. A dark pixel might be A and LT, span style equals color blue, and GT, 1 and LT slash span and GT, and a light pixel A and LT, span style equals color blue, and GT, 0 and LT slash span and GT. Or, for shades of gray, numbers between and LT, span style equals color blue, and GT, 0 and LT slash span and GT, and LT, span style equals color blue, and GT, 1 and LT slash span and GT. So, our handwritten 7 is transformed into a long list of numbers. This list, this and LT, span style equals color blue, and GT, vector of pixel values and LT slash span and GT, is the raw input data for our computer. But how does the computer turn this list of numbers into the decision, this is a 7? To begin, let's consider the simplest possible decision-making unit, a single neuron. Not a biological neuron, but a computational one. Imagine it as a tiny processing node, designed to make a very simple yes or no decision. This neuron takes in R and LT, span style equals color blue, and GT, pixel values and LT slash span and GT, as input. But not all pixels are equally important for recognizing a 7. For instance, the pixels forming the top horizontal bar are crucial. The pixels in the bottom left corner, where a 7 usually isn't, are less so. This is where and LT, span style equals color green, and GT, weights and LT slash span and GT, come in. Each input connection has A and LT, span style equals color green, and GT, weight and LT slash span and GT, a number that tells the neuron how important that particular pixel is for its decision. A large and LT, span style equals color green, and GT, positive weight and LT slash span and GT, means this pixel strongly suggests a 7 dot. A large and LT, span style equals color green, and GT, negative weight and LT slash span and GT, means this pixel strongly suggests not a 7 dot. The neuron multiplies each and LT, span style equals color blue, and GT, input pixel value and LT slash span and GT, by its corresponding and LT, span style equals color green, and GT, weight and LT slash span and GT. Then, it sums up all these weighted inputs. This sum tells us the overall evidence for a 7 based on the pixels it's looking at. But there's one more piece, the and LT, span style equals color yellow, and GT, bias and LT slash span and GT. Think of the and LT, span style equals color yellow, and GT, bias and LT/span and GT, as a baseline enthusiasm. Even if the weighted sum is slightly low, a positive and LT, span style equals color yellow, and GT, bias and LT/span and GT, can push the neuron closer to saying yes. A negative and LT, span style equals color yellow, and GT, bias and LT/span and GT, makes it harder to say yes. It's a threshold adjustment. So, the neuron calculates, and LT, span style equals color red, and GT, sum equals input 1 times weight 1, plus input 2 times weight 2, plus bias and LT/span and GT. This sum is its raw opinion. Finally, the neuron needs to make a decision, yes or no. This is done by an and LT, span style equals color yellow, and GT, activation function and LT/span and GT. It takes the sum and squashes it into a simple output, often between and LT, span style equals color red, and GT, 0 and LT/span and GT, and LT, span style equals color red, and GT, 1 and LT/span and GT. If the sum is high enough, it outputs A and LT, span style equals color red, and GT, 1 and LT/span and GT, yes, it's a 7. If not, it outputs A and LT, span style equals color red, and GT, 0 and LT/span and GT, no, it's not. This single neuron can learn to recognize a very simple pattern, like is there a horizontal line at the top? But a 7 is more complex than that. It has a diagonal stroke, and a vertical stroke. A single neuron can't capture all that nuance. This is why we need and LT, span style equals color yellow, and GT, layers and LT/span and GT, of neurons, forming A and LT, span style equals color yellow, and GT, neural network and LT/span and GT. Instead of one neuron making a complex decision, we have many simple neurons, each looking for a tiny piece of the puzzle. The first layer of neurons might specialize in detecting basic features. Is there a horizontal line here? Is there a diagonal line there? Each neuron in this and LT, span style equals color